So next theorem is our maximum power transfer theorem. Okay. So what does this maximum power transfer theorem tells us? It should be known to us. So firstly, I am going to read out its definition. Then we will derive this theorem, and then we will go for the numerical part. Okay. So first is the de- derivation. So a resistive load served through a resistive network will abstract the maximum power when the load resistance value is same as the resistance viewed by the load as it looks back into the network. Okay, so this is also called the output resistance of the network, or the resistance presented to the output terminals of the network. Okay, so looking at the definition, we can make out that the resistance which is viewed by the load and into the network is same as the thevenin resistance or Norton resistance. Okay, so the resistive load will extract or abstract maximum power from the energy source when the load resistance is equal to Norton resistance. Okay, so this is the main interpretation of the maximum power transfer theorem. Okay, so now we will derive this theorem. So first of all, consider a generator. You can consider a generator or DC battery source. It is same. Why it is represented as a generator? Just to emphasize that the magnitude of the battery source is less. It is generally taken in the circuits as 10 volts, 5 volts, 20, 50 volts. Okay, and also we can observe at our house, at our homes, when we are having the inverters. So the battery source is less, 24 volts or 48 volts, or maybe multiple of 1.5 volts or 6 volts. Okay, so the but if we are using the DC generator, it means that it can have the greater magnitude of voltage. Okay, so and also what does this suggest? If we are having the less amount of voltage source, then it is used for distribution purpose only, because we are having UPS at home, we are having the mobile batteries at home, we are having inverters at home, but it is used within the home. Okay, or you can say that it is being used at the distribution level. If you go slightly above it, if the magnitude is raised, you can say that okay, you are living in a multi-story building of say 150 flats, and there is a power backup. Okay, so if there is a power backup, then there must be some DG set at the ground level of the building. Okay, so this DG set is providing the conditioned backup supply. Again, this is used for a distribution level only, because that DG set is dedicated to provide the power backup to say same 150 flats. Okay, but now if we go further above, some DC generator is there and its magnitude is large. Okay, so then we can consider the transmission of the DC as well. At present, what you are likely to see or what you observe, the transmission towers you observe. Okay, so these transmission towers, these supply the three-phase power. This is the earth wire, and these are the RYB three phases. Okay, so it is again connected to a second tower, but this is the AC transmission, not the DC transmission. Okay, what we are used to see. But if the transmission level is up, then this generator is also used to supply the DC power or DC voltage for the transmission lines. Okay, and what it will serve? It will serve the load. At present, we are used to see the load as bulb, tube light, AC, fan, etc. Okay, right. It is not problem. But if we go further, then the whole Jaipur or whole Jodhpur is considered as one load center or a one bigger load. Okay, or you can say the industrial area or our whole university is considered as a one load. Okay, so if the voltage magnitude is increasing, we can say that load is also increasing. Our interpretation of the load is also changing. Okay, so let us assume that this EMF generated by this DC generator is EG, and it is having some RO internal resistance. Okay, and so this is the internal resistance of the generator, plus you can see if there is a some resistance between the conductors, that is also clubbed to this resistance RO. Okay, so if we apply the Ohm's law, V is equal to IR, we will get the current which is flowing into the circuit or to the load will be Eg upon R naught plus RL. Okay, so this is the current which is supplied. So the power delivered will be I square R, you are well aware. So this value of the current is substituted in this formula to get these results. Okay, but our main agenda is that the power transfer should be maximum. Okay, to make the power transfer maximum, what we do the first order differentiation with respect to the variable and substitute it to 0. So what is the variable resistance here? Variable resistance is the load resistance. because the internal resistance remains same, and the resistance between the two lines of the conductors also remains same. Okay, so dp upon drl is equal to 0. When we do the first order differentiation, what result we get? We get RL equal to R naught. Okay, so if the circuit is simpler, then the internal resistance is equal to load resistance, and we will get the maximum power transferred. Okay, so this value is substituted here to get the final result as this. Okay, so but if this circuit is complicated, then there are more than more resistance are there and few resistance are in series and few are in parallel, then the effective resistance will be the Thevenin resistance. Okay, here only one resistance is there, so you can say that okay, this is the Thevenin resistance, because if the load resistance is removed, this is the resistance which we will get. Okay, but if the circuit is a bit complicated, then we are required to replace this by Thevenin resistance. Okay, so this voltage source can be removed and also changed to a current source, because as I have just told you that it is also applicable for this Thevenin resistance and Norton resistance are equivalent. So we can say that the current circuit can also be changed into this parallel combination of the load resistance, or here this load resistance is replaced by inverse of the load resistance, which is the conductance. This is experimentally calculated. So again, this GT is nothing but the inverse of the Thevenin resistance. Okay, and current source is there. So we can now conclude in this theorem as that the power transferred is equal to the, if the circuit is simpler, then we can go for the EG or this generator EMF, and if the circuit is complicated, series and parallel combinations are required, then the voltage is replaced by the open circuit voltage, because we are already calculating the Thevenin resistance also. Okay, so in terms of the conductance, we can say that for a current source, the power transfer will be maximum when the load conductance is equal to the source conductance. Okay, so in this case, it is changed like this. Okay, nothing complicated. Simple V is equal to IR formula is applied here, nothing more than that. You can say, okay, this is the voltage, so this is 4 remains same. V is equal to IR, so I square R square, you can say. And this one of this is become the short circuit current, and one load resistance is already present, so it will be cut, and this resistance is replaced by 1 by conductance, so it becomes like this.